Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. And here you have information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. Let me note that for exam P manual, I also have an additional set of practice exams. So there are 20 practice exams in the manual for exam P, and then another set of exams, 11 exams in the new edition for the 2020, which should be available in early November. So if you go to this website for the exam P manual, this link will take you to the Actuarial Bookstore website where you can find information about my exam P manual. You can there also just search for 11 additional practice exams for exam P and find that as an additional set. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's a problem for today for exam IFM. Investments in financial markets. You use the usual method in McDonald, that means McDonald book written by McDonald, which is the textbook for exam IFM, and well, one of the textbooks, but the main one really, and the following information to construct a one-period binomial tree modeling the price movements of a non-dividend paying stock. The tree is sometimes called a forward tree. The period is 3 months. The initial stock price is 100. The stock's volatility is 30%. The continuously compounded risk-free interest rate is 4%. At the beginning of the period, an investor owns an American put option on the stock. The option expires at the end of the period. Determine the smallest integer valued strike price for which an investor will exercise the put option at the beginning of the period. So immediately. And here's the solution. The problem asks us to find the smallest integer k satisfying the inequality, as you see here, where k minus s, which is the payoff upon immediate exercise, is greater than the expected present value of payoff at expiration under risk-neutral valuation, which is the present value factor e to the minus rh times the probability that the stock will go up and then multiply by maximum p star, the probability of an up move in the stock. And then that's multiplied by the maximum of k minus su0 plus 1 minus p star times the maximum of k minus sd0. So basically, the probability of an up move times the payoff in that state if the stock moves up, plus 1 minus the probability of an up move, so the probability of a down move times the payoff in that down move. And all of this is discounted to today. And this is the value of the option if ends up being exercised at the end of the period. Let us call the above inequality star. We have the following data about it. As the initial stock price is known to be 100, the up move in this model is given by the formula e to the r minus delta times h plus sigma square root of h. And delta is 0, so this is e to the rh plus sigma square root of h. Delta is 0 because the stock does not pay any dividends. And this, we just plug in the known numbers. So sigma is known to be 0.3, r is known to be 0.04, and the period of time is 3 months, so a quarter of a year, so 0.25. And this is e to the 0.16, so 1.1735. So in the up move, a dollar invested in one share of, I'm sorry, in not a one, we don't actually 100. So dollar invested in this stock will rise to a dollar 0.1735. The down move is e to the r minus delta h minus sigma square root of h, so the same thing as above, but with a minus sigma square root of h. This ends up being e to the negative 0.16, and that's approximately 0.8694. P star, the property of the up move, is e to the r minus delta h minus d over u minus h. This e to the r minus delta h, that's sort of a replacement for 1 plus the risk-free rate factor over the period of time of length h, but of course adjusted for the dividend yield, and the dividend is 0, so it's not terribly complicated. But we plug in with all of the formulas for all of this, and this actually simplifies to 1 minus e to the minus sigma square root of h over e to the sigma square root of h minus e to the minus sigma square root of h, and we just simplify this by multiplying the top and the bottom by e to the sigma square root of h, and we end up with e to the sigma square root of h minus 1 over e to the 2 sigma square root of h. Now, of course, e to the 2 sigma square root of h is the square of e to the sigma square root of h, and 1 is the square of 1. So the top is like a minus b, and the bottom is a squared minus b squared. And a squared minus b squared is equal to a plus b times a minus b. I call this the Chechnya formula. You better memorize it. So that this ends up being 1 over e to the sigma square root of h plus 1. And we plug in the numbers, and that's approximately 0.4626, and 1 minus that is approximately 0.5374. And now this inequality star that we're working on becomes k minus s is greater than e to the minus 0.01. It's e to the minus 0.04, but over a quarter of a year. So to the power 1/4, so e to the minus 0.01 times 0.4626 times the maximum of k minus 117.35 or 0, plus 0.5374 times the maximum of k minus 86.94 and 0. And we consider 3 cases. K is less than or equal to 86.94, k greater than or equal to 117.35, and k between the two. For k less than or equal to 86.94, this inequality star cannot hold because the left-hand side is less than 0 and its right-hand side is equal to 0. For k greater than or equal to 117.35, inequality, again, I should have called it star, my apologies, always holds because the left-hand side is k minus 100, while the right-hand side is e to the minus 0.01, k minus 100. For k between 86.94, this inequality star becomes k minus s is greater than e to the minus 0.01 times 0.5374 times k minus 86.94. And now we basically solve this for k, and k becomes greater than 100 minus e to the minus 0.01 times 0.5374 times 86.94 over 1 minus e to the minus 0.01 times 0.5374. That's approximately 114.85. And so we don't have to go all the way above 117.35. We just need to be above 114.85, and so the answer is 115. That's answer B. Please remember this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.